fundamental principles of monitoring instrumentation. That is the headline given in Miller. So what we have to talk about only the fundamental principles and not exactly how each and every monitor works. If you start writing all those details, then you won't find time to complete the answer in your theory paper. So we'll just stick to the basics, fundamentals. So analysis, why we should know about the fundamental principles of the monitoring instrumentation is the first question. So anesthesiologists must be able not only to understand and interpret the data from monitor, but also anticipate and recognize errors. You must know when a monitor is not functioning properly and it is giving a false error and false reading. So that is the reason why we must know the fundamental principles of how they are working. So the basic principles involve nature of physics and measurement. So physics is a science of matter and energy. That is the interaction between the two. So physics is quantitative and mathematics is the language of physics, which is the weak point for all medical graduates. So the calculus is the mathematical tool for expressing and studying the laws of physics. So we must know whether the monitor is having an accuracy and precision of measurements. Now, what is accuracy? It is how close a value is to the true value is called accurate or accuracy. For example, if a person's normal blood pressure is supposed to be 120/80 and your monitor is able to read 118 to 78, that is almost close to the true value. Whereas some non-invasive BP monitors, if you take three readings, it will give three different values. Then you cannot say it is accurate. Whereas precision of a measurement or is how repeatable the measurements are, which of course Jay Bharti mentioned that this is the difference between the two. So don't think that accuracy and precision mean the same. It is not. Accuracy is how close the value and how dependable the value is to the normal true value. And precision is how you can repeat the measurements. And a physiological measurement is dependable only if it is accurate to the degree required for clinical decision making. So the monitor should be more accurate. But blood pressure measured using sphygmomanometer and stethoscope, oscillometric automated non-invasive device, and intra-arterial cannula placement, all the three may not be equal. Each has different source of error. So our choice may be determined by accuracy or by a need for frequency of data and ease of retrieving the data. So if you want, you are doing a minor case like hernia and you want to measure the blood pressure, you just want it to be accurate so that you will know whether there is a hypotension after spinal or not. Whereas if you are doing a cardiac case, you need to put in an arterial catheter so that you can repeatedly measure it again and again and have a data going on. So it helps you to determine what type of monitoring you have to use by knowing the difference between accuracy and precision. Okay, that is the basis. The required accuracy of a clinical monitor is determined by the smallest change in measured variable that could affect the clinical decision. So, for example, after a spinal, if there is a fall in BP, if the monitor is accurate, you know when to treat it and when to just, wait and just give fluids and see whether it comes back again to normal. So that decision making is usually requires an accurate monitor. And the requirement of absolute accuracy is the measured value correct. That is the question that you have. Maybe different from the requirement for relative accuracy, whether the measured value follows the trend. So these are the two important decisions or differences that you should know between absolute accuracy and relative accuracy. Now the measurement of mass is involved in our basic principles of instrumentation. When we weigh a patient, we are determining the force of gravity acting on the patient's mass. So when we measure CVP using a manometer, we are observing the balance of forces between the patient's venous pressure and the force of gravity acting on the fluid column. This is the basis. So the older technique of CVP measurement, we used to have this manometer connected to the CVP central venous catheter, and there will be a intravenous fluid bag, and there is a three-way stopcock, which is a very important part of the whole setup. So by adjusting the balancing the forces between the fluid column and the patient's blood column, we are able to measure the CVP. So this is how the pressures are managed. The hydrostatic forces acting on that. This is the water column, which is being pushed by the patient's blood flow or the blood column to raise the water in the manometer so that you can measure the height and calculate the CVP. So this is how we were measuring the CVP earlier. But after the advent of electronic devices, we no more use all these manometers and all that. We straight away connect it to the electronic circuit, which has a Wheatstone bridge, and that works on the principle described by her. By the there are 4 resistors, 3 known and 1 unknown. So balancing this will tell you what is the potential difference and by which you can measure, and the display comes including the waveform. So you cannot get a waveform in the manometer. Every time you have to turn the stopcock. This is how we were trained in the earlier days when we want to measure the CVP. There was used to be one Solomon Victor's CVP monitor stand attached to the IV fluid stand, and we used to connect it and then measure this. But nowadays we got this electronically measuring Wheatstone bridges available, and that is become more easier. Then coming to the measurement of energy, E is equal to mc squared. That is the famous formula by Albert Einstein and the theory of special relativity. So energy are the same physical entity and can be changed into each energy. And so in equation, the increase in the mass of body times the speed of light squared is equal to kinetic energy of that body. So that is the important equation which you have to know. The fundamental law of conversion of energy, that energy and matter can neither be created or destroyed. It can only change from one form to another. It's the basis of understanding many anesthesia monitors. Then coming to signal processing and information theory, what is when a quantity varies over time, it is said to contain a signal. And recording of vital signals in patient data first began when Harvey Cushing did it for his surgeries by plotting patients' vital parameters like pulse, blood pressure, respiration, temperature, which nurses helped to analyze them later to find out the cause of any untoward incidences. But later we started collecting it through various other means, including our aims, and the data that we collected were processed. The analog signal is amplified in the background of noise and desired signal are amplified. This is called the signal to noise ratio. This is one of the important basic fundamentals that we have to know. So whenever your signal is also coming along with the background noise from the machine should be able to amplify the signal so that you can correctly measure or interpret the signal rather than the noise. So this signal to noise ratio should be quite good so that signal will be projected better than the noise. This calls for the need to employ what is called enhancing the signal to noise ratio, for which you can use filters, which are so this is the analog signal which is converted into a digital signal like this. So when this happens, the background noises will be curtailed. So filters are used to remove the noise, improving the quality of signal. And in some cases, a desired periodic signal can be repeated and summated, and so that accompanying random noises becomes a smaller fraction to the signal. And this is the basis of what is called the evoke potential, which she mentioned as ensemble averaging. So many signals are summated or added together, and all the unwanted noises are filtered, and you get a uh, improved signal quality, which is called ensemble averaging. The waveform of any periodic signal can be represented by summation of sinusoidal waves called Fourier series. So a waveform originally expressed as amplitude versus time is transformed into a plot of power versus frequency, and that is called the power spectrum. So this is this form of display is seen in EEG, and error in signal analysis which can have or aliasing occurs when the sampling frequency is too slow to capture the rapid variations of true signals. This happens with ultrasound machines where display may show echoes from objects that do not actually exist. So you can get an artifact like that. Another example of signal distortion is during IABP due to damping and resonance of the signal, which all of you know. Damping means underpulp playing and resonance means exaggerating. So in modern monitors, data is not only recorded but stored. Problems that happen by this are security breach, potential loss of data, and erroneous signal processing leading to faulty algorithm and mistakes in patient care. So measurements commonly made during anesthesia are pressure measurement using transducer or signal process pressure measurement like NIBP, measurements using sound energy, passive sound energy like stethoscope, active sound energy like echo and Doppler and percussion, measurements using electric energy, that is EEG and ECG, and active electric examination, neuromuscular block every time you stimulate, and SSP, and measurements using light energy. It's multifunctional tool using Beer-Lambert rod and pulse oximeter and is processed in absorption monitor, and simple absorption capnometry and anesthetic vapor analyzer. Signal artifact management. Most difficult engineering problem in pulse oximeter is the identification of the fluctuation and absorption pattern of arterial blood among EMG, that is electromagnetic force and other factors. There are four reasons for this: ambient light, low perfusion. So when a pulse oximeter is not working properly or giving a correct reading, you must be able to identify what are all the causes. It may be ambient light, low perfusion, venous pulsation, or added light absorbers. And all these produce a low signal to noise ratio. That is, the noise is exaggerated, signal is underplayed, so you don't get a proper signal. Then coming to measurement of temperature, the kinetic energy of a molecule and the atoms is called temperature, and the molecular motion, whether it is translational, vibrational, or rotational, ceases. The substance is said to be at a temperature of absolute zero, which is the lowest possible temperature, which is minus 273 degrees centigrade. This state provides the reference point for all temperature measurements. So temperature monitors can be thermometers, thermistors, thermopile, or liquid crystal. And next is the measurement of flow. Flow refers to volume of fluid passing through a point. So square meter by seconds, or flow velocity, that is speed of a fluid at a particular point measured in millisecond. So this example of highway with lot of cars, velocity is akin to the speed of the individual car. So when you talk about fluid velocity, you are talking about the speed with which the fluid flows, and flow is akin to the total number of cars going. So the total volume of fluid flowing. These are the two things which are important for all our mass of fluid and flow volume meters like Eurometer, volumeter, and all that. And dilutional flow meters are dilute immersion and thick principle. Velocity and pressure flow meters include Venturi and Picard. And balanced pressure flow meters are torque tube and Borden tube. So these are the various types of flow meters that we are using. So you can just see this picture to understand about the variable arc torque tube. And this is the Borden gauge that is used. And kinetic energy flow meters are used in Wright's respirometer. So respirometer, this is the basic thing. In some hospitals, still this respirometer may be available, and in the Viva, they may give this instrument and ask you to describe the machine and where it is used for all those measurements. So if we just mention these one-liners for this, I think that is more than enough instead of going into detailed description of every instrument that is you are using, how they are working. If you start writing all that, I think you will be short of time. So for the question, fundamental principles of the measurement in monitoring instrumentation, I think you just have to mention the basic principle, physics involved in the machine, and you can complete the answer, and I think that will be more than enough.